So we're going to look at enthalpy questions today, starting off with this one here. So pause the video and try it yourself first, and then I'll go through how to do it. So this one tells you, it says calculate the enthalpy of formation of ethanol. It gives you the formula of ethanol given the following enthalpies of combustion. So you've got these different enthalpies of combustion down here. So the best way to start this sort of question is you need to write down the equation for the enthalpy change you're trying to calculate. So you're trying to calculate the enthalpy of formation of ethanol. So write down the equation for that. It requires you to know the definitions very well. You need to know the definition for enthalpy of formation, of combustion, what bond enthalpy, just very quickly, and you need to know them in detail. So the enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states. So I've got my ethanol, I put that on the right hand side because I'm forming it. So the arrow is going towards the thing that you are forming. We're forming the ethanol. On the left hand side, I'm going to put the elements that I need to form it. So I need carbon, hydrogen, and oxygen. But all the elements have to be in their standard state. You don't just find oxygen on its own, you find oxygen as O2. So we have to write O2. Same for hydrogen, it's diatomic, O2. Carbon is found on its own. Well, ish. It's actually found bonded to other carbons in things like graphite or diamond. So we've got our oxygen, our hydrogen, and our carbon. We need to put in their standard states, or their state symbols for each of these. So obviously, I'm sure you know that oxygen is a gas, hydrogen is a gas, carbon is going to be a solid, and this tells you this is going to be a liquid. Finally, we need to make sure it's all balanced. When you're balancing these things, it's always good to start with the carbon, these organic compounds. So carbon, we've got 2 carbons there, so we'll put 2 there. Then the hydrogen, so we've got 3, 2, so 6 hydrogens, so we'll put 3 there, then 6 hydrogens. Now, you might be thinking, hang on a minute, we've got 2 oxygens here and 1 oxygen here. So you might be thinking, okay, let's put a 2 here. That would be the incorrect thing to do. The reason for that is because of the definition of formation. So if you think back to the definition of formation is the enthalpy change when 1 mole of a substance is formed. 1 mole, not 2 moles. So if we put a 2 here, it's no longer the enthalpy of formation. It's the enthalpy of formation times 2. So this has to be a 1 in front of here. So how are we going to get this oxygen to be the same as over here? Well, it's easy. We just use a half. So we've got 2 oxygens here. We put a half in front of it. We now have 1 oxygen. So now we have the equation for the enthalpy of formation of ethanol. Okay, the next step is, well, there's 2 ways you can do it. You can do the shortcut method, which is using an equation, or you can do the long way, which is doing the enthalpy cycle. You actually need to know both. You need to be able to use the shortcut when you can, but sometimes, in some of the more difficult questions, the shortcut will not work, and you need to be able to construct a cycle. Also in the question could ask you for a cycle, so you do need to be comfortable for drawing cycles. So we'll do the shortcut first, and then we'll do the cycle. So the shortcut, it goes like this. What you do is you look at the data that you've been given. As you can see, all of the data you've been given is combustion data. It's all combustion data. If it's all combustion data, what I want you to think is I want you to think crap. So combustion is reactants minus products. So you think crap. So the shortcut is going to be delta H, that's this, equals the sum of all the delta HC of the reactants minus the sum of all the delta HC of the products. So you've got delta HC equals the sum of, that's this symbol here is the sum of delta HC reactants minus the sum of delta HC products. So write that exactly as it's shown here, and that's often worth 1 mark. Now, all we have to do is take our numbers up here and put them into our equation. So you can see we've got our reactants. So our reactants are are oxygen, hydrogen and carbon. So we've got the data here for combustion for carbon, so we'll do carbon first. So as you can see, when you burn 1 mole of carbon, it gives out 393 kilojoules per mole of energy. So we put it as minus 393. But we're not burning 1 mole of carbon. If you look, we actually have 2 moles of carbon, so we have to multiply this by 2. Hydrogen. So hydrogen is minus 286, but we're not burning 1 mole of hydrogen molecules, we're burning 3 moles of hydrogen molecules, so we take that number and times it by 3. And there's our reactants. You might be thinking, what about oxygen? Well, think about it. If you burn oxygen, what do you make? I mean, combustion is adding oxygen. So if you add oxygen to oxygen, there's no reaction that takes place. So no energy is given out or taken in. No bonds are broken or formed. So there is no combustion value for oxygen, so we don't need to include it. Okay, now we do our products. So our products are just the ethanol. We've just got that one value there, so minus the products. So I'll do the products in brackets here. So it's minus, there's that minus there, and the value for the ethanol is minus 1371. So all we need to do now is to throw these all into a calculator to get an answer for delta H, being very careful to watch out for this point here, because you can see you've got minus and minus, so as we know, 2 minuses make a plus. So throw that all into a calculator and you get minus 253 kilojoules per mole. And that is the enthalpy of formation of ethanol. So you can see it's an exothermic process making ethanol from the elements in their standard states. If we wanted to construct a cycle, if the question asked us to construct a cycle, or perhaps the question was more difficult, say it involved 2 types of data, not just combustion data, then we do it like this. Again, we write out the enthalpy of formation on the top. Basically, the one that you want to work out, it's good to put it on top. So we're now going to construct an enthalpy cycle, and the reason it works is like this. The enthalpy change, going from all of these guys to this, is the same if we go a different route. So basically what that means is that if you think about what is this enthalpy change? Well, this enthalpy change is worked out from how much energy it takes to break the bonds compared to how much energy is given out when bonds are formed. So if we go down here and form some different bonds and break some different bonds, but we end up going back to here, so we go down to here, break some bonds, form some bonds, over here, break some bonds, form some bonds. The end of the day, the energy which is given out or taken in is going to be the same. So it's independent of the route taken. Now this is only, of course, if we keep the same number of elements. So going down, what we're going to do, we're going to keep the same number of hydrogens, the same number of carbons, same number of oxygens. And what this is essentially just another equation just drawn at a dodgy angle. The reason the arrow is pointing down, away from the hydrogen and the carbon, is all due to the data that we've been given. So if you look at the data, we've been given combustion data. So we're going from a situation where all of these substances are not chemically combined with oxygen towards a situation where they are chemically combined with oxygen, because that is what combustion is. It's adding oxygen. So down here, if we add oxygen to carbon, what do we get? Well, we get carbon dioxide. If we add oxygen to hydrogen, what do we get? We get water. If we add oxygen to oxygen, well, we just get oxygen, nothing really happens. So we've got to balance it now again. So we've got 3 hydrogens up there, so well 6 in total, so we need 6 down here. We've got 2 carbons there, so we need 2 here. So you now might spot the oxygens no longer balanced. So down here we've got 7 oxygens, so 4 oxygens here, 3 oxygens here, so 7 oxygens. So what we'll need to do is we need to change this so that we also have 7 oxygens here, and we also need 7 in total over here as well. So you can see I've now changed, so I've now got 7 over 2, so I've got 7 oxygens here, 7 oxygens down here, got 1 over here, so I'll just pop another 6 oxygens here, so 3O2. Okay, we now need a line, an arrow connecting here, and here. So, which way does the arrow go? Well, what you need to do is you need to look at the data that you've been given. So you've been given combustion data for the ethanol. So we're going from a situation where ethanol is not chemically combined with oxygen, well, not the products of combustion, towards a situation where it is the products of combustion. So we're going from here down to the products of combustion. So it looks like this. So there is our enthalpy cycle. We just need to put the values in now. So you can see that this enthalpy change here, combusting one ethanol, gives out this energy. So that's minus 1371. Over here, we've got burning 2 carbons, so that's 2 times minus 393, and we're also combusting 3 hydrogens, so 3 times minus 286. So you might see in books a few different ways to sort of get this all into an equation. My favourite way is this way. So basically it's the clockwise anti-clockwise rule. So you have put down clockwise equals anti-clockwise. So all this means is that all the clockwise arrows will equal all the anti-clockwise arrows. So if you look, you can see that this one here is going clockwise, this arrow here. This one here is also going clockwise. And this one's going anti-clockwise. This one here is going anti-clockwise. So clockwise we've got delta H, we've got minus 1371, those are our 2 clockwise arrows, and our anti-clockwise arrow is all of this stuff. So if we calculate all of that together, that comes all out to minus 1644. Okay, if we get delta H on its own, so if we just take this number here and put it at the other side, we get the same as before. We get minus 273 kilojoules per mole.